So I'm happy to welcome Els Peeters from the University of Western Ontario, who will be telling us about the photochemical evolution of pHs in space. So Els got her PhD in 2002 from the Captain Institute at University of Groningen. And then she moved on to NASA Ames and was also associated with the SETI Institute while she was there. And finally, following this, she moved into University of Western Ontario, where she has been now for quite a number of years, progressing up through the ranks. And in 2019, she became full professor there. So on the sideline, I guess I met Els Peeters first quite early in my career in astrochemistry, and I've always seen her as an expert within the area, especially of the PAHs and observations of PAHs in space, where she has made many major contributions and is really one of the main experts in this area. So we look very much forward, Els, to your presentation on pHs in space, observations of pHs in space, and their photochemical evolution. Thank you for being here today.
Thank you very much for this nice introduction. Let me share my screen. So if it's all good, you can see my slides?
Yes.
Awesome.
And we will be recording this lecture, I should say. So please turn off your sound, and if you don't want to have your image recorded, also turn off your video. Thank you.
Okay, so as Liv was saying already, I would give you a little bit of a perspective of what we know from observations of pHs in space. And so you're probably all aware of what pHs are, polycyclic aromatic hydrocarbons. And so what that means, you see some structures of some example pH molecules on the left. So you have a carbon skeleton with hydrogen on the edges. I have to say for the entire talk, we're going to talk about pHs in not the chemical definition, but rather in the way astronomers use the term pHs. And so what does that mean? It basically means you have your pHs as defined by the chemical definition, but that you could also make some changes. You can change a hydrogen with the side group. You can change a carbon atom with, for example, a nitrogen atom. And so all of these related molecules, cousins, are also taken into the term of the pHs for astronomers. And so the most common way that we observe them in space is through their vibrational emission. And so on the right here, you see an infrared spectrum from a star-forming region, the Ryan bar. And so everything you see in red, or which is colored in red, are these broad features, and those are assigned to the pH family. And you can see on top of the figure that you, excuse me, that you can see what the different band assignments are for the individual features. And so the other thing to be aware of is that this pH emission feature sits on top of a dust continuum emission, which is highlighted in yellow. And depending on who you talk or which paper you're reading, the pH features also sit on top of these plateaus, which are these broad bumps indicated by the arrows. Sometimes in literature, these plateaus are taken as the base of the Laurentian or Drude wings of the features themselves. And so if you go into space, pH resides in PDRs, and PDR stands for photodissociation regions. And what does that mean? It basically means you're looking at regions in space between the stars, typically in the interstellar medium, where the far UV photons dominate the physics and chemistry. And so far UV photons, we think here about photons with an energy between 6 eV and 13.6 eV. 13.6 eV is the ionization potential of hydrogen. And if you look at the interstellar medium, so the region between the stars, you typically designate regions depending on the state in which you can find hydrogen. Hydrogen is the most abundant element in space. And so if you look at the little cartoon at the bottom on the left-hand side, you see a cluster of massive stars which have very strong and hard radiation field. So they emit lots of UV photons. And so in the surroundings, they're able to ionize hydrogen. And so you create an H2 region. So a region where hydrogen is fully ionized. At some point, you reach a boundary, a very sharp boundary, which is denoted as the ionization front, after which you can find hydrogen in a neutral state. And if you go a little bit further away from your ionizing stars, you cross the dissociation front. That's where you convert your neutral hydrogen to molecular hydrogen. And so if you're talking about the photodissociation region, you take all the neutral gas, so neutral hydrogen gas, and a large fraction of the molecular hydrogen gas. And so PDRs are very prolific in space. You can find them clearly surrounding young massive stars. You can find them in diffuse clouds. So you can have a cloud which is illuminated from the outside. That edge of that cloud will also give you a PDR. Protoplanetary disks, reflection nebula, planetary nebula. So these are nebula which are basically with some young and intermediate mass stars. If they grow old, they emit their outer layers. And when the central core or the remaining core becomes very hot, in some cases it can ionize these previously expelled layers and form a planetary nebula. And then, of course, also in galaxies, star-forming galaxies, normal galaxies, ultra-luminous galaxies, a large variety of galaxies. You also see PDRs. And so that means if you're going to look, if PDRs are so prevalent in the universe, it shouldn't surprise you that the pH emission, so the infrared emission that we refer to as pH emission, is widespread. It is very abundant. And you can see in the images that are shown in the bottom, on the left-hand side, you see a star-forming region. And so all of these images are multicolor images, and I show you the key in that spectrum shown on the right. So you basically have a multi-composite image of 4 colors. And so each color represents a certain broadband filter. And so you can see that the red color and the orange color is really dominated by our strong emission features of pHs. And so if you look at these composite images, wherever you see kind of a reddish color, it basically indicates that you have these vibrational emission features of the pH molecules. And so clearly from the figures shown here, these are all taken with the Spitzer Space Telescope. You can see that pH emission is widespread, not only in a star-forming region in our own Milky Way, but if you just look at different galaxies, you can also see widespread emission. They are abundant, and if you look at, for example, the galaxy on the right-hand side, it's a spiral galaxy. For those type of galaxies, the pH emission can easily be up to 10 or 15% of the total power output across all wavelengths for these galaxies. So they really emit a lot of energy that is emitted by these galaxies. So they're widespread and abundant. And so it shouldn't surprise you that they also play an important role in several physical and chemical processes. For example, if you have a pH molecule, you can photoionize it, and that free electron can carry away the excess energy, collide with other particles in the gas, and in that way heat the gas. And so we know that these small molecules are a dominant heating source in the neutral ISM. So the neutral ISM is where hydrogen is in neutral form. And so they set the temperature in these regions. They partake in chemical reactions and influence the charge balance. And so they influence the abundances of elements and molecules. And also these pH molecules are flat molecules, planar molecules, and so they have very large surface areas, and so they can participate in surface chemistry or provide the surface area for surface chemistry. And so these are just a few examples in which way that pHs contribute on a microscopic scale. But that means, because they're widespread and abundant, that they also contribute or are important in large-scale processes. For example, star and planet formation. I already mentioned that pHs are the main heating source for the neutral ISM. And so you can think of protoplanetary disk around just a young star. And so the surface layer of that protoplanetary disk, the temperature is set by these pH molecules. The evolution of the interstellar medium is also set by these microscopic processes, and also galaxy evolution, because galaxy evolution is very dependent on the star formation that's going on. And we already saw that pH, these microscopic processes influence large-scale processes such as star formation. However, in order to fully quantify what the role is of pHs in these microscopic processes and completely model it, you really need to know a detailed knowledge of the pH population. And so when we talk about the pH population, we talk about not a single pH molecule, but a family of molecules. And we would like to know what their composition is. And so at this point, it's not known, it's still debated whether you are talking about many different molecules, millions or more. So a very large family of pH molecules, or on the other alternative is that you talk about the survivor of the fittest. And so that's referred to as the grandpa hypothesis. And so either one could be true. We don't know at this point. But it's important to realize that we're talking about more than a single molecule. We're talking about, in the grand pi hypothesis, the hypothesis say that we have about, an order of 10 pH molecules that dominate the emission. In the case for the very large pH family, of course, you can have very large numbers of molecules. Now, if you look at the population, what do you want to know? It's, for example, the charge balance. So the charge balance of your pH population will depend on the radiation field, as well as the temperature of the gas and the electron density, because that's important for recombination. And so you can imagine, for example, here I show you a little figure that calculates the fraction of each charge state for a given molecule with distance from a radiation source. And you can see that the charge balance changes depending on the specific position you are with respect to that radiation source, is in this case a star. And so the charge balance is something that we are interested in when we want to characterize a pH population, but of course also the size distribution. Are we talking about pH molecules which have 20 carbon atoms, 50 carbon atoms, 100 carbon atoms? I mentioned the word here, size distribution, so it probably means we have some kind of distribution or variation in the size. Not all the molecules in the population will have the same size. And as you can imagine, if you have different sizes of pHs, each of these different pHs will have a different charge balance because ionization potential will be different, etc. And then finally, if you want to talk about the position, we really want to know, ideally, we want to know which specific pH molecules are present. But we also, so that's the molecular structure, but we also very often, especially for observations, we look at the edge structure. And I show you some specific edge structures in these structures here on the right. And so you can have zigzag edges or armchair edges. We have Bay regions, so where we have, which is shown in the top molecule. And then also for the hydrogens, which are attached to the carbon skeleton, we talk about different positions. For example, the solo CH hydrogen. So that means the corresponding or the next neighbor carbon atoms do not have a bond with hydrogen. For dual CH groups, you have two hydrogens which are connected to neighboring carbon atoms, etc. And so if you want to characterize a population, we want to know as much as possible about these different parameters here. And I'm sure you're all aware that recently we have identified the first small pH molecules in space. This was not through infrared spectroscopy. This was in the radio. So we're not looking at vibrational emission there. And so this is very good news, very exciting news. But the main way of detecting pH emission in space at this point is still in the infrared. And in the infrared, the emission is vibrational emission. And so it's not very sensitive to the specific molecule. And so they overlap. That's on one hand why the emission is so strong. But it means that characterizing its pH population is far more challenging. And so I'm going to show you a few examples of what we know or how we can characterize or derive something about the PAH population from observations. And so the first thing I would like to show is basically we're going to look at infrared spectra of two reflection nebula. So on the top one, you have NGC 2023 and NGC 7023 is on the bottom. These are my two favorite sources for this talk. And we know from the spectra that we obtained with the Spitzer Space Telescope that the pH emission in this reflection nebula is changing from position to position. And so you see these three rectangular boxes, and within those boxes, we have basically a spectrum at every pixel. And what we've done is we have calculated the fluxes of the main PAH bands. Spitzer only started at 5 microns. So we have the 6.2, 7, 7, 8, 6, 11, 0, and 11.2 micrometer band. And we did a principal component analysis on these fluxes. And the principal component analysis is basically, so we have as input 5 variables or the fluxes of the 5 different pH bands. And the principal component analysis is going to look for a set of independent variables that can explain all the variation that you see in the spectra. So that means each of the inputs pH bands or the fluxes of these bands is then a linear combination of the principal components that come out of this analysis. Why do you want to do this type of analysis? First of all, it can reduce the dimensionality of your problem. So we are starting with 5 variables, and so we're wondering if we need 5 variables. And secondly, these two, the results of these principal components that come out of this analysis, they're independent variables. And so if we apply that to these two reflection nebula, we basically see 2 main principal components. And they're shown here on the right. So on the x-axis, you have the most important principal component. And what does that mean? It's that component can explain the largest fraction of the variation that you see in the spectra. And on the y-axis, you'd see the second most important principal component. And so if you look and you see at these errors that are shown in this plot, what is it shown? If you project each of these errors on the x-axis, it will tell you how that particular component depends on the first principal component. And for both reflection and you see that if the first principal component increases, then you have that the fluxes of all the 5 bands that we are considering are all increasing. And you can see that there is a split. You have 2 groups. You have one that is the 11.2, which is kind of unique or isolated. And then you have the other 4 bands, which are more clustered together. And so if you look at the first component, I already mentioned that all the fluxes increases and the principal component increases. And so the first component basically probes the amount of total pH emission you have. And so you can also see that here in this correlation plot, where we plot the principal component with respect to the total path flux, and you see we have a very tight correlation. Now, the amount of pH emission depends on 2 parameters. First of all, is the pH abundance, and also the pH excitation. Okay. Because the pH molecules need to absorb some energy before they can emit. So it's not surprising that the amount of pH emission is the most important component. So let's have a look now at the second principal component. And the second principal component, if you look at the biplots, so the 2 figures on the right, you can already mention that 11.2 was kind of isolated and the other bands were more grouped together. Now you can see how each of these bands depend on PC2 by looking at the projection of each error on the y-axis. And so you can see in that sense that if PC2 increases, 11.2 increases, but that's not the case for the other bands. In fact, some of them actually will decrease. And so we already know from lab data and theoretical data that 11.2 is typically assigned to neutral pH molecules, while the others are assigned to ionic pH molecules. And so we looked at the correlation plot of the PC2 with a tracer shown as 11.0 over 11.2. And this is not as tight as correlation as we had for the amount of pH emission, but you see that there is some dependence. And so PC2 has some relation to the charge balance of the pH molecules. And in hindsight, the fact that that's the second component is really not that surprising, because we know from early on, from laboratory data of neutral and ionic pHs, that the neutral pHs have quite distinct spectrum from the ionic pHs. So the neutral pHs have very strong emission around 3 micron and 11 micron, while the ionized paths will have a strong emission between 6 and 9 micron. And this is something that we see very easily in observations, because we have these so-called well-known, very tight correlations between the 6.2 and the 7.7, as shown here for a galaxy M82, but also between 6.2 and 8.6 and 7.7 and 8.6. These are very tight correlations, and we see them in all observations. They always come back. And so these observations are typically, if you bundle it together, what we know. This is once again the Orion spectrum from the first slide. And so from the observations, we find that the 3.3 and 11.2 correlate with each other, and that 6.2, 7.7, 8.6, and 11.0 correlate with each other, which is basically a perfect match if you look at how neutral and ionized pHs emit, based on the lab data that we have here on the left-hand side. What is surprising, though, from this PCA analysis is that we have 2 parameters, so 2 principal components, the total amount of pH emission and the charge state of pH. And those 2 alone explain 98% of the variance in the fluxes that we are considering. And so then you can wonder, like, okay, but if they explain 98% of the variation, how do we ever learn something more about the PAR population that goes beyond the charge state of the pHs? And so that's a valid question that we shall explore next. So can we, for example, find the probe for pH size? If you take two pHs and they have different sizes, the relative strength of their emission features depend on the size. And the reason for that is that the relative strength of the bands is strongly influenced by the excitation temperature of the molecule, and the excitation temperature depends on the size of the molecule if they absorb the same photon energy. And so you can see that in these two spectra here very clearly, if you just compare the 3.3 on the left-hand side versus over the 11.2, and you can see for the small pH that the ratio, the peak intensity is very similar compared for the large pH molecule shown here. Most of the emission is emitted at longer wavelengths. And so the relative strength of the pH band depends on the size. And of course, because it's kind of relative to each other, you want to have the baseline in wavelength as large as possible, so 3.3 over 11.2 is most sensitive to changing in excitation and path size, while bands which are closer to each other will be less sensitive to it. However, we have already seen that pH charge is the main parameter that governs the intensities of the main pH bands. And so if you want to find a tracer for size, independent of this charge, we need to use bands that are assigned to the same charge state. And so if you look back to our initial laboratory data of small PAR molecules, that means you can ask yourself if the 3.3 and 11.2 would be a good tracer for size, or because they both come from neutral paths, or if the 6.2, 7, 7, 8, 6 are a tracer for size because they all originate from ionized paths. And that's something that you can actually check. So if you go to the NASA Ames pH infrared spectral database, this is a database of a large number of theoretical calculated spectra of pH molecules, as well as experimental spectra. We here consider only the theoretical spectra, and you can basically submit all of these pHs to a given radiation field and calculate what the emission spectrum is, and then see what the ratio of the 6.2 or 7.7 is. And if you look at that ratio in function of size, which is given on the x-axis, you can see that the either for neutrals or cations, doesn't matter. There is really not a dependence on path size. And so one of the reasons is because those two bands are very close to each other, and so they are intrinsically already less sensitive to path size. And the other reason is that, the pH structure is comes a little bit into play on how these molecules emit in this region. And so 6.2 over 7.7 is not a tracer for path size. However, it has been used extensively on Spitzer data because Spitzer had only access starting at 5 micron and longer wavelengths. And so we could not explore the other tracer, which is the 3.3 and 11.2. And so you can do the same calculations based on theoretical spectra and calculate what the 3.3 over 11.2 is for a given energy, photon energy that is absorbed. And you can see here that you see a very nice relationship between this ratio of these two bands and path and the size of the number of carbon atoms. And so 3 over 11.2 is a good tracer of path size. However, as I mentioned, the 3.3 was not available with Spitzer data. And so this was a major drawback if you're working with Spitzer data. Now, you can also use these theoretical data then to kind of make a diagnostic. We already know that 3.3 and 11.2 comes from neutrals and 6.27786 from ions. And we also now know that 3.3 and 11.3 basically traces the size. And so you can make this plot all the ions, or sorry, all the molecules in the database, and you can calculate once again the ratios shown here. So it's 11 micron over 3.3 on the x-axis and 11 micron over 7.7 on the y-axis. And you can see that we nicely divide out the ions and the neutrals. So the top kind of curve are the neutrals and the lower curve are the ions. And from left to right, you go from small pHs to large pHs as indicated by the color code of the symbol. And so you can make some kind of grid that is shown on the right-hand side, where you change the fraction for the charge. So you go from fully neutral to fully cationic. And you also change the size. And then you can come up with some kind of diagnostic diagram to probe the charge and the size of your emitting pH molecule. So that's based on theoretical data. Does it work with observations? So we looked to our 2 reflection nebula, and we obtained some additional data from Sophia to observe the 3.3 micron. And so the field of view for which we have obtained data is the blue box. And you see this light blue line in both images on the bottom that tells you the cut that is shown in the x-axis on the 2 top panels. And so from the left to the right on these figures, we go from close to the illuminating star to further away. And you can see that both the 3.3 and 11.2 changes with distance from the star, and they both peak at what we call the PDR front. And so that's basically traced by the peak of the molecular hydrogen emission. So where you have the dissociation front. But you also see from these figures that the relative variation of these 2 pH bands vary with distance. And so you can take the ratio, and then we found that we do detect changes in these ratios for both. These changes are higher, closer to the star, and are lowest when you are basically at the PDR front. And so for each of these reflection nebula, we know the star, which is responsible for the radiation field. So we can calculate what the average photon energy is that our pH molecules will see. And so with that, and based on the theoretical data that I showed in the previous slide, you can calculate what the corresponding path size is. So we see that the path size varies with distance from the star. On the right-hand side for 7023, we have this peak in the middle at about 38 arc seconds from the star. But if you look at the line in the image below it, you can see we have this circle below the brightest region, which is the PDR front. The origin of the circle is not known as far as I am aware. And so that's where we also have this local peak. So the image there is a little bit complicated because of the presence of this circle. Nevertheless, so we have variation with distance from the star. The smallest path size is seen on the PDR front. If you compare the 2 reflection nebula, the radiation field is quite different, as shown on the right in the table, in the right column. And the corresponding path size, you can see, is also different across the entire cut. And so for NGC 7023, where we have the weakest radiation field, the pH size across the entire cuts are smaller than what we've seen in 2022. And so basically both of these factors, that first of all, size varies with distance from the star, and also if we compare the two reflection nebula, lets us to conclude that UV fields lead to increased photoprocessing of pHs, and so they destroy the smallest pHs and therefore increase the average size of the pHs probed. So now we know that we have a good tracer for charge, we have a good tracer for size. Can we extract another parameter, a third parameter from the pH emission that we observe? And so let's come back here on the left spectrum. We have our famous figure again of the Ryan bar, color-coded with the main charge states for the main bands. So we have 3, 3, and 11, 2 in blue for the neutrals, and 6, 2, 7, 7, 8, 6 in red for the ions. And so what we did is we were going to look at the single charge state now. So now we're going to look at the ionic bands. And we took the strongest region of a pH emission between 7 and 9 microns. It's known that we have the 7.7. It's known that it has two components, one peaking at 7.6 and one peaking around 7.8. We have also a third pH emission band at 8.6. And so what we did is we decomposed this emission between 7 and 9 microns by 4 Gaussian. And we needed the fourth Gaussian because you see we have some kind of bridge between the 7.7 and 8.6, which is not covered by just fitting it by 2 Gaussians. And so if this entire emission comes from is assigned to ionic bands or ionic pHs, and so if charge is the only parameter, what you would expect if you look at the morphology of each of these 4 Gaussian is that it's exactly the same, because there's only one parameter that is responsible for all that emission. So if you cut it up in any way you want, you would always find the same morphology. So if you do that once again for our reflection nebula 2023, we have 2 fields, one in the north and one in the south. So that's shown in the left image of our reflection nebula. And on the right, you see that we have the morphology for the 4 components of our decomposition. The top row is for the north field of view, the bottom row for the south field of view. And you can see that the morphology between those 4 components in a given field of view is quite distinct. The middle 2, 7.8 and 8.2, are very similar, and the outer 2, the 7.6 and 8.6, are very similar. But they don't compare very well with each other. And so despite that all the emission comes from what we believe is ionic pH emission, if you decompose that emission, you can see that there is something else going on. And so there is, in addition to charge, there has to be another parameter that influences that emission. And so if you go and kind of look at the morphology for all the individual pH components in this reflection nebula, you can order it starting with where the peak emission is closest to the star to further away from the star. So on the top of our list here, we have the emission features which are peaking closest to the star. And if you go down the list, you have emission features peaking further away from the star. I haven't talked about all of these emission features, but you can see on the second last row that we have the 11.2, which we assign to neutral pH emission. And then you can see in red color, so in the dashed boxes, that we have the ionic bands, and they, as we already saw in the previous slide, they actually behave differently. Their morphology is differently and peak at different distances from the star. The Gaussian components that we discussed in the previous slide, you have two components which are on the second line. The outer two components, they peak very close to the central star, but the inner two components, they peak furthest away from the star, where we see emission from the plateaus underlying the features, as well as the 11.2, which is assigned to neutral pH. And this is something that we actually see also when we look at this PCA analysis I was talking about earlier. Because if you look at these biplots again on the right-hand side here for the two reflection nebula, and we look at the projection on the y-axis, because that was the one that we felt traces the charge. You can see that if you go from most negative value to projection to a positive projection, you go from 11.0 to 8.6, 7.7, and 6.2. Exactly the same as what we saw in that spatial sequence by looking at the morphologies. So we have our ionic bands, and they behave differently, despite showing very tight correlations between them. And so what could be the origin of this behavior? So there are three different options for this. The first one is basically astronomers up to now basically talk about neutral pHs and ionized pHs. And we do not make the distinction between the different, singly ionized pHs, doubly ionized pHs, and so on, because we just observationally so far we could never do that. And so it could be that because the 6.2 and 7.7 are peaking slightly further away from the ionizing star, that they're overall are less ionized than the 8.6 and 11.0. So it means that you're kind of now getting to the point that you can probe differences in charge balance beyond neutral and ion. Another option for the different flavors is that to the emission between 7 and 9 microns, you have contribution of Park clusters and nanoparticles. And the reason why this is an option is because if you look at the inner two bands at 7.8 and 8.2, they were peaking at the same distance from the star as the plateau emission. And the plateau emission has typically been assigned to Park clusters or nanoparticles. And so that means that potentially the inner two components could have a similar carrier. And then finally, another option could be is that you're tracing the edge structure of pHs. And so on the right-hand side, you can see a figure illustrating that. So what we have different theoretical spectra, and they're numbered from 0 up to 6, and that number indicates the number of bays that you have in your molecule. So in the bottom structure that is shown in the middle, you see you have no bay regions, and so that corresponds to the 0. And then you start removing some bonds to create these bay regions, calculate the spectra, and we go up to 6 bay regions. And you can see that for the bottom spectrum, you have an emission peak at 7.8 and 8.6. But if you go to a higher number of bays, those two peaks merge towards each other and finally merge completely and peak around 8 microns. And so it could be that the edge structure also has some role in the emission to the 6.2 and the 7.7, but less so to the 8.6 and 11.0. Which of the three is the origin of these different ionic flavors is currently not settled. Now, let's go back to our PCA analysis. And so what you see is that you have your PCA analysis for the other reflection nebula. And here the clustering of the 6.2 and 7.7 was not so strong compared to the other clusters. So what we did is we divided the reflection nebula to basically just tracing the PDR front or the filament in the green box, and the cavity, so surrounding the star, there is a low density area, which is referred to as a cavity. And we did the analysis of these two distinct regions separately. And so what we found is that we do see this distinct behavior of the ionic bands very clearly in the PDR, but it's not present in the cavity. And so our second principal component, so which explained the second largest variation in the spectra, is different between the PDR and the cavity. And so if you look at the second component for the cavity, you can see if you do the projections one again on the y-axis, we first have a positive projections, means you have talking about the solo CH out of plane bending mode. If you go to lower values, you go to the CH in plane bending mode, and for very negative, you go to the CC stretching mode. And so this second principal component probe changes probably in either molecular structure and or hydrogenation. And so here again, we see that we can actually start probing the pH population beyond the charge and the size. I see I'm speaking very slowly, so let me quickly talk to you about the star-forming region, the Orion Nebula. And so what you see is that a little cartoon here. So we have very massive stars, the trapeziums, which are ionizing their surrounding area. And so in their surrounding area, you have first an H2 region, so where the ionized gas, where the hydrogen is fully ionized, shown in red here, or squared. Then you have the dotted region, which is your PDR, and then the striped region is the molecular cloud. And the Orion bar is the region where the green area is kind of vertical. And this is important because I showed you that PDRs, you have this nice layered structure going from fully ionized to neutral hydrogen and molecular hydrogen, etc. And so if you see a PDR edge on, that means you can actually see this structure. So the Orion bar is a very popular source for observations. In addition to the bar, you can see behind, on the left-hand side of the bar and on the right-hand side of the bar in the cartoon, we have a face on PDR where we basically see everything from the ionized reach, all the different stratifications, all the different layers in a single line of sight. And so we do see, if you look at the observations, that we have this stratification in the Orion bar. We have the ionized gas on the left-hand side in that left figure. Then we have all the curves shown here in color are pH emission curves. And so they all peak at the same distance from the trapezium cluster. And then the dashed dotted line in gray shows you the molecular hydrogen. So we see the stratification. We are certain that we can, or we confirm that with our observations, we can see the edge, the stratification in the edge on PDR. And so what we're going to do is we have two slits across this edge here, and we're going to trace in the right-hand figure here the dust continuum emission across those two slits. And we are once again looking at the stratification of our PDR. So we have the ionized gas on the left of the light colored gray. In between the two gray colors, we have neutral gas, and the dark gray area shows you the peak of the molecular hydrogen emission. Now, when I talk about the H2 emission, it's important to realize, if you look at the cartoon, it's basically the area left from where you can see the PDR edge on, so where the green area is vertical. And so you have some PDR emission behind the ionized region. And so if we see pH emission there, it's not coming from the ionized gas necessarily, but it's dominated from the back wall of the PDR there. And so when we look at the emission between the main ionic bands, which is always very tight, if you do that for this data, you can see we have actually very weak emission. And so in this color plot, everything which is basically from the left side of the edge on PDRs up to the ionization front in the light gray color is colored in red, and everything on the right-hand side is colored in blue. And so you see that they're all mixed with each other, and there's no such thing as a very nice tight correlation. So we did a different distribution or color coding, and we asked ourselves, maybe the edge on PDR is different from the other regions. So in the H2 region, where we have a phase on PDR in the deck, and beyond the Orion bar, where we also see this phase on PDR. And so it works better, but you can see that we still have some blue points that are mixed in with the red points. So the only way where we can have a very nice correlation between the two is if you take the edge on PDR separately for one particular slit. And so then that is colored in blue. You can see that we have a very nice correlation. We still have some scattered in the red points, but the red points now are a mixture. So it includes both phase on PDRs in front of the bar, so closer to the trapezium and beyond the bar. And it also includes the edge on PDR of one slit, which seems to be slightly more similar to phase on PDR than what we have for the other slit. And so it seems that the PDR viewing angle influences the observed correlation. You know, this is supposed to be H6 versus 6.2 is two ionic bands. There's supposed to be extremely tight correlations. And this, if you look at all the points in our slits, you don't see that. Now, if you look at pH emission for different regions, it's not just the viewing angle of the PDR, which will influence your results. It's also the type of interstellar medium you're looking at. Are you looking to a star-forming region? Are you looking to reflection? And are you looking to the diffuse ISM? They all behave differently in these plots. And I'll show you just two examples here. On the left-hand side, you see comparison between star-forming regions in red and reflection nebula in purple. And you see that the correlation for the star-forming regions is very different than that for the reflection nebula. On the right-hand side, we go to another reflection nebula and we compare we do correlation plots on the complete right-hand side, and they're color-coded according to the map that is shown, which shows you the 8.6 over 11.2. And so all the colors from green, yellow, orange, red are basically coming from the reflection nebula itself and form a very nice correlation. But our map was bigger than that, and we also looked outside of our nebula, and these are color-coded in blue, and you can see that they form a completely different correlation. And so these are just two simple examples showing that if you're looking at even within the ISM, at different environments, your correlations or the emission, your pH emission will behave differently. And so I hope I have shown you a little bit of a hint of that we can actually now probe our PA population, not just the charge, the size, but also some other parameters like molecular structure, although the exact origin is not entirely clear at this point. And so that means if you look at an extended region, you can actually probe the evolution of the PA population if you combine your observations, of course, with theoretical data and laboratory data. Now, what all of the work that I've shown you so far is done with Spitzer data. Spitzer had a very low spectral resolution, and so cannot distinguish between all the subcomponents of the different pH bands. And so here I showed you some older data in the 3 micron region, as well as in the 7 to 9 micron region from higher spectral resolution data. And you can see that we do see a lot of substructure, which we basically were unable to probe at this point. However, the future is very bright. JWST is around the corner, hopefully to be launched at the end of this year. And there we basically get simultaneously a high spatial resolution, a long wavelength coverage, ideal for pH and emission studies, at medium spectral resolution, so we can decipher all this substructure, and at very high sensitivity. And so just to give you an idea of how well or how improved the JWST will be compared to Spitzer, so you can look at the bottom cartoon here on the figure in panel C, where you see the stratification of the PDR, so going from the ionized gas, the H2 region, you cross the ionization front, after which your hydrogen becomes neutral. Then you cross the dissociation front, where you have the peak of the molecular hydrogen, and then you go into the molecular zone. And so on the right-hand side of that panel, you see the beam that we had for Spitzer. And so with Spitzer, all of these different regions is basically in a single pixel and are all mixed together. The beam for JWST is shown as well. And so with JWST, if your source is nearby and edge on, you can actually probe the different stratifications individually and then figure out how the pH emission changes and what are the underlying processes for it. And so in that regard, you probably have heard that there is an early release science program on James Webb, which will study the Orion bar. And so we are very eager to look forward to our observations, hopefully to be taken next year in September. And so we will do near spec, so spectroscopic IFU, so integral field unit mosaics from 1 to 28 microns, and we will also do imaging. And so I cannot stress that from the observational point of view, JWST is just ideally suited to study pH emission. It will be a gold mine. Of course, the interpretation of this data cannot happen without the corresponding work in laboratories, as well as the theoretical studies. And so I hope to encourage you all to work extensively on pH properties in whatever your expertise is, so that we can combine all our expertise and basically bring the pH knowledge in space to the next level. And with that, I think I talk a long time, so I leave this slide up with my main conclusions. But before, let me briefly thank my collaborators. So I showed you a lot of work from my former PhD student, Colin Knight, my current PhD student, Amik Sidhu, and my former postdoc, Alexander Smaragudakis. And so they did most of the work, and you may have seen them already before on some pH workshops. And with that, I thank you for your attention. I thank you.